So to sketch this function, I'm going to have to go through and I'm going to have to identify what all of those numbers do to the basic shape, as well as which basic shape it is. So looking up at this function here, I have a square root symbol there. That means that it's a radical function, and radicals are the ones that look sort of like this, the fallen over parabola. So there are 4 numbers up there. So I'm going to look for the ones that are additions or subtractions. So those are these 2 here. Anything that are additions or subtractions are translations, which just move the thing around. So this plus 5, because it's a plus inside of the operator, that's a leftward shift, 5. This one out here is a negative outside of the operator. That makes it a downward shift. And if I look inside the operator, I see a multiplication factor of 2, and the outside is a multiplication factor of 3. These 2 numbers are transformations, so they're going to actually change, they're going to stretch it or compress it, whatever they do. A factor of 2 inside the operator is a compression by a factor of 2. Horizontally. And the 3 in front is a stretch by a factor of 3 vertically. Ugh. So I'm going to first draw my untranslated axis. There's my y. And here's my x. So just like in the translation section, I'm going to draw a translated set of axes that are moved left 5 and down 4. So my y-axis, 1, 2, 3, 4, 5 to the left. And my x-axis down 4, 1, 2, 3, 4. So now that that's there, I'm going to take this basic pattern and I'm just going to put the dots on before I start doing any transformations. So the basic pattern for a radical was at the origin, 0, 0, 1 and 1, 1, 2, 3, 4, and 2. I'm getting these from the square roots of x. So the square root of 1 is 1. The square root of 4 is 2. The next one would be 9, has a clean square root. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Square root of 9 is 3. And then 16, 10, 11, 12, 13, 14, 15, 16, and 4. This is the basic untransformed pattern. I now need to apply these 2 transformations to it. So pick a dot. Start with this one. It needs to be twice as close to the translated axis, and it needs to be twice as far up from the translated axis, so that one's not going to go anywhere. Anything on the origin is unaffected by transformations. This dot should be half as far, but so half as far from the y-axis, but thrice as far from the x. So that would be here. 1 times 3 is 3, and a half of 1 is a half. This dot is 4 and 2. Half of this would be 2. 3 of this would be 6. So 2 and 1, 2, 3, 4, 5, 6. This one is 9 and 3. Half of 9 is 4.5. 3 times 3 is 9, so I should be at 4.5 and 9. 3, 4.5, and 1, 2, 3, 4, 5, 6, 7, 8, 9. This one is at 16 and 4. Half of 16 would be 8. 3 of 4 would be 12. So I should be at 8 and 12. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this radical function, after having been translated and then transformed, looks something like this. Now, it is good practice, once you've done a sketch, to find the y-intercept for the function. Finding the y-intercept allows you to check that the line that you just drew in there is approximately in the correct space. So for this function, if I put in 0, f at 0, I end up with 3 square root of 2 and 0 plus 5 minus 4. So if I were to fetch a calculator then, carrying out order of operations, 0 plus 5 is 5. 2 times 5 is 10. The square root of 10 is 3.16 times 3 is 9.48 minus 4 is 5.486. So this function evaluated when x equals 0 gives me 5.486. So I'm going to go back and I'm going to check the original untranslated axis and see if, when x is 0 on those axes, if this function is crossing at 5.486 on the y. So here's my original axes. That's where x is 0. If I go up 1, 2, 3, 4, 5.5, I'm there, which is exactly where this function has passed through. So by checking the y-intercept, I've been able to confirm that I've sketched this one correctly. So to sketch this one, looking at it, I see a bunch of numbers here, but I see a 2 flying up there. That means that this is a parabola, a squared function. Parabolas look like this. So I'm going to hunt through this line. I'm going to find my addition and subtraction factors. There they are. The one inside the operator is a horizontal translation. A negative inside the operator is a rightward shift. So this function has been shifted right 4. An addition outside of the operator is an upward shift. This has been moved up 6. And I'm going to hunt for my multiplication factors. That's these two here. The 1/3 on the inside is a horizontal compression or stretch. So a factor of 1/3 means my x's are 1/3 as effective. So I'm going to be 3 times as far from the y-axis. So it's a horizontal stretch by 3. By a factor of 3. And this 2 in front means that the heights will be doubled. The negative is telling you that it's been flipped across the axis, reflected. So this is a vertical stretch. And reflection by 2. So I will get my untranslated axis on my grid here. And y. My x. I'm going to translate my axes. I need to go right 4 and up 6. So 1, 2, 3, 4. That's here. And up 6. 1, 2, 3, 4, 5, 6. So from there, I'm going to draw my basic pattern. So for a parabola, the vertex sits at 0, 0. Then, because it's a square, I'm squaring my x values to get the y's. So 1 squared would be 1, 2 squared would be 4, 3 squared would be 9. It's off my grid. 1 squared is 1, negative 2 squared is 4, negative 3 squared is 9. So it's off my grid again. Now I'm going to go through this dot by dot in order to find out where the transformations carry them. Anything that's on the origin stays on the origin. So this dot here needs to be 3 times as far from the y-axis. So instead of 1 square, it's now 3 squares. It needs to be reflected, so instead of 1 above, it's 1 below. And then its height or depth needs to be doubled. So instead of 1, it's 2. So this dot was thrice as far from the y-axis, reflected, and then twice as far from the x-axis. Same thing is going to happen to this one. Thrice as far. Instead of 1, it's 3. Reflect it, and then make it twice as far. And end up here. This dot is 2 away from the y-axis and 4 away from the x. Thrice this would be there at 6. Reflect it, and then double its height to here. So instead of 2, I'm 6, and instead of 4 above, I'm 8 below. Same will happen to this dot. Instead of 2, it needs to be 6. Instead of above, it needs to be a 1, 2, 3, 4, 5, 6. Instead of above, it needs to be below. And instead of 4, it needs to be doubled to 8. You can sketch in the parabola. And as is good practice, anytime you sketch something that has been translated and transformed, I'm going to investigate the y-axis. Sorry, this function was g. G at 0 would be minus 2, 1/3 of 0 minus 4 squared plus 6. So executing these operations in the correct order, 0 minus 4. 0 minus 4 is negative 4 times 1/3. It's negative 1.3333. Square it. It's 1.777 times negative 2. It's negative 3.5555 plus 6. So a total of 2.44. So on the original untranslated axis, when x is 0, the y should be about 2.5. So finding 0 on that axis, going up 1, 2.5. That's exactly where I've got it. So I know that I've sketched this function correctly. So this function, I look in here, I have a 2 with a bunch of stuff up in an exponent. That makes it an exponential. So exponentials look like this. So I look for my addition and subtraction modifiers. Those are there. Those are my translations. A positive inside the operator is a leftward shift. This is left 5. And a negative outside of the operator is a downward shift. That's down 6. Then I go hunting for my multiplication factors. I see a 1/3 out front and a negative 1/4 up in here. A 1/3 in front, a fraction out there, a number less than 1. is a vertical compression by a factor of 3. And a fraction inside of the function is a horizontal stretch. Because the x's are a quarter as effective as they normally would be, it's going to take 4 times as long to get the same effect. So it's going to be a horizontal stretch. In addition to that, there is a negative in here, which means it is reflected horizontally. So a horizontal reflection and stretch by 4, by a factor of 4. All right, so my untranslated axis going to have to move my axis left 5 and down 6. 1, 2, 3, 4, 5. And down 6. 1, 2, 3, 4, 5, 6. So my basic pattern for a base 2 exponential at 0 for all exponentials, anything to the exponent 0 is 1. And then I'm doubling it each time. 2 to the 1 would be 2. 2 squared would be 4. 2 cubed would be 8. 2 to the power 4 is 16. 9, 10, 11, 12, 13, 14, 15. 2 to the negative 1 is a half, and then a quarter, and then an eighth, etc. So I'm going to start moving my dots. We're going to start with this one. Now it is not on the origin, so unlike the last 2 examples, this first dot I move is going to have to move because it's not right there in the center. If I try and make this 3 times farther from the y-axis, 4 times farther from the y-axis, it has nowhere to go, but I can compress its height by a third. So instead of 1, I'd be at a third. This one here, I need to reflect it horizontally. So instead of on the right, it's now on the left. I need to quadruple its distance. So instead of 1, I'm at 4. 1, 2, 3, 4. And I need to divide its height by 3. 2 divided by 3 is 2/3, something like that. This dot here is up 4 and 2 out. So reflect it horizontally. Quadruple that distance would be 2, 4, 6, 8. And divide its height by 3. 4 divided by 3 is 1 and a bit. Leave it there. This dot is going to be off my grid, so I'm not going to worry about it. And these dots are forming the tail. So take this one, reflect it, quadruple its distance. So instead of 1, it's 1, 2, 3, 4, and divide its height by 3. It's already half. A third of a half is a sixth, so that's real low. This dot is 2 out, so reflect it, quadruple it, so it's 2, 4, 6, 8. It was already at a quarter. A third of a quarter is a twelfth, so that's real low. So I end up with an exponential that looks something like this. Nice and flat. All right. So as always, you should investigate your y-intercepts. So h at 0 would be 1/3, 2, -1/4, 0 plus 5, minus 6. So I grab a calculator and doing these things in the correct order. 0 plus 5 is 5 times negative 1/4 is negative 1.25. 2 to that exponent is 0.42044 divided by 3 or times 1/3, however you want to look at that, minus 6 gives me negative 5.859. So when I look at my untranslated axis, when I'm at x equals 0 here, I should be at negative 1, 2, 3, 4, 5, and almost 6, which I am. So I know I've translated this properly. So I have a logarithm here. Logarithms have a long tail from infinity and then gradually grow that way. So looking inside there, I have my addition and subtraction factors. That will be a rightward shift 6 and an upward shift 1. Looking at my multiplication factors, I have a vertical stretch by a factor of 5 with a reflection. I have a horizontal compression because the x's are twice as effective, also with a reflection. So I'm going to have a vertical stretch, vertical reflection and stretch, and a horizontal compression and reflection. So especially with the logarithm, because it's one you're maybe not as familiar with, I want to just take this drawing and execute these reflections on it so we've got a rough idea what we're looking at. If this thing is vertically reflected, instead of coming from negative infinity and growing, if I flip that, it's going to drop from infinity and grow that way. So once I apply the vertical reflection, this thing is going to look like this. Right, the vertical asymptote will be going up now instead of down. The thing will be dropping like so. Once I execute a horizontal reflection on it, I have to take this and I have to flip it that way. So it's still dropping from above, from infinity as a vertical asymptote, but instead of swinging to the right, it's going to swing to the left. So when I'm done, this thing should look sort of like that, like a lazy J. Get my untranslated axis on here. And then I'm going to translate my axis. So I need to go right 6 and up 1. 1, 2, 3, 4, 5, 6. And up 1. So I'm going to put the basic dots on. If you will permit me, I'm just going to do this reflection. So a logarithm should be crossing here. Actually, I'll say let's do the reflection. Should be here, and then at point 1 should be there. Point 2, so it's got your vertical asymptote like this, and I don't have another dot until 10 on the x-axis. So if I were to take this and reflect it horizontally and then vertically, that one doesn't move. This one, reflected horizontally, ends up just here on the left side of the y-axis, and then flipped vertically, it ends up above it instead of below it. This one, flipped horizontally to the other side, flipped vertically to the other side. It's like this. Now this dot way over here at 10 and 1 if I flip it this way, would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 1. So that's flipped horizontally. Now flip it vertically, it would be here. Next dot is at 100, so we're not going to worry about it. You can see that basic logarithm showing up there. Now that I've got them reflected, I'm going to try and do the stretches and compressions. So I need to make it 5 times farther from the y-axis, but half as far from the x. So this one here, half as far would be here. This one, half as far, would be at 5 squares instead of 10. So 1, 2, 3, 4, 5. And if I quintuple the height, instead of 1, I'm at 1, 2, 3, 4, 5. That's here. This dot, half as far from the y-axis, would be immeasurably close. But then 5 times as far would put it 1, 2, 3, 4, 5. We'd be putting it there. So I end up with a logarithm that looks something like this. And it will take off like so. As is always good practice, we're going to check the y-intercept to see where it is. So j at 0 would be minus 5 log negative 2, 0 minus 6 plus 1. So carrying these operations out in correct order, 0 minus 6 is negative 6 times negative 2 is 12. Log of 12 is 1.079 times negative 5 is negative 5.39 plus 1 is negative 4.396. So if I go to my untranslated axis at 0, that's here, I should find my y-intercept at negative 1, 2, 3, 4, and a bit, which indeed I do. So I have sketched this one correctly.
The last function we have to sketch here with all of the transformations and translations is a sine or a cosine. So most of the stuff is the same. I still have a shift in the horizontal direction and a shift in the vertical direction. So I'm going to translate my axis. I have built a scale here that jumps by 30 degrees every square and up by half every square. We talked about that in the translations and the transformation section for cosine. That choice just gives you a nice proportionality of the curve. So I need to translate my x-axis up 1, find 1. I'm going to draw myself a line. And I need to shift rightward 45 degrees. So if that's 0 and that's 90, 45 is halfway between them. All right. Now from there, you need a sort of doodle, a rough idea of what the shape looks like. So the cosine pattern starts high, ends high, troughs in the center, and then zeroes out dead center between those two things. So it's kind of like this. So these numbers here, the 3 and the 2, those are going to stretch this curve this way, and it's going to affect the curve that way. So because this pattern repeats over and over and over again, we're going to have to figure out exactly how long this will be this way and how tall it will be this way so that we can repeat that pattern many times. So I want to deal with the vertical first because it's the most straightforward. A cosine curve usually rises 1 and troughs at 1. But this cosine curve has been amplified by a factor of 3. That means its peaks will be 3 times as high and its troughs will be 3 times as deep. So when I'm drawing this wave, it's going to rise 1, 2, 3 from the midline. So I'm just going to draw a line in there showing you where all my peaks are going to land. So when I'm drawing the peaks, they have to come up and touch this green line up here. The troughs will be 3 units below this midline. So 1, 2, 3. All right. So when I start to draw this curve, wherever it starts, I'm going to be hitting peaks on that line, zeroing here, troughing it on this green line, zeroing back here again, and then peaking back up at the top line. So now that that's done, something you need to remember about these patterns for both sine and cosine is they take 360 degrees to execute a full cycle. That's just like a circle. 360 degrees in a circle, that's not coincidence. So from this translated axis, I'm going to count 360 degrees this way. So at 30 each, we'd have 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. I'm going to cut it off there. I missed the square. That should be 1.5 in from 360, which is here. Okay. Now that I've got that little box drawn in there that's 360 degrees long, I can think about this number. That 2 says there are twice as many waves in the same amount of space. That number there affects the speed of the function. The bigger this is, the faster the dots happen. So if you have a wave that used to be this long and you make it twice as fast, it should be done its full cycle in not much space. So if I have to fit 2 of them into this box, the first thing I'm going to do is just cut this box in half. So it's that would be counting 180 degrees, so 30, 60, 90, 120, 150, 180 would be here. I'm going to draw myself another line, like so. So that's showing me 2 waves in 360 degrees. And it looks like every 1, 2, 3, 4, 5, 6 blocks, every 6 blocks I'm going to have to map this pattern in. So I'm just going to keep drawing these horizontal or vertical lines every 6 blocks. 1, 2, 3, 4, 5, 6. Because I'll need another full wave pattern there. And then 1, 2, 3, 4, 5, 6. I'll need another full wave pattern in there. And it's not 6 squares. 6 squares isn't important. It's that is the number of squares in half of 360 degrees. Okay, so you should see in this grid here a whole pile of rectangles. Here's one, here's one, here's one. Into each of these rectangles, I have to map this pattern. So you just pick a rectangle. I'm going to choose this one. Start high, end high. Right, that's what cosine does. Troughs in the middle. It's right there. And then it zeroes out dead center between your peak and your trough. So that's going to be there and there. So now that I've got those 5 dots, I'm going to be able to connect them like so. That's one segment of the wave. I just need to keep copying that pattern over and over and over again in these boxes until I end up with a wave that covers the whole grid. So start high, end high, trough dead center, zero out halfway on each of those. Start high, end high, zero out halfway, wait, trough halfway, zero out halfway between those. Start high, end high, trough dead center, zero out halfway between those, and I can connect in my nice continuous way. There you go. So the cosines and sines are a little different than the other ones you've been sketching just because it has this repeated pattern. So you need to know how often the pattern repeats. In order to do that, you just construct yourself some scaffolding. You draw a line at where the peaks will be, draw a line at where the troughs will be. Take your 360 degrees and chop it up into that many chunks. Draw them in. And then you just have to map your sine or your cosine pattern into each rectangle.